Hello, everyone. Welcome to the Spectral Geometry in the Cloud. So it's a pleasure to have Vladimir Medvedev with us today. So we will talk about free boundary minimal surfaces in geodesic ball in hemisphere and HN. So as usual, if you have any question, you can unmute yourself or put it in the chat and we will let Vladimir about your question. Okay, so the floor is yours, please.
So Asma, thank you very much for the introduction. And first of all, I'd like to thank the organizer of this very nice seminar, Alexander Giroir and Asma Hassanijad, who invited me to give a talk here. As Asma already said, I'm going to talk about free boundary minimal submanifolds, FBMS for shorthand. And I'm going to start with definitions. Just a quick reminder, what is a free boundary minimal submanifold? So so I'm going to start with MG is a Riemannian manifold, which is supposed to be which has an empty boundary, and we consider another manifold sigma, which can have dimension k, and its immersion into that manifold MG. And to any this immersion, one can associate the volume of this immersion, which is given by this formula, and but we also allow. So we also want the boundary of sigma to be the boundary to do not leave the boundary of M of the ambient manifold. And the picture is as follows. For example, here MG is our manifold and sigma is somewhere here. And the boundary of sigma can slide along the boundary of M. This is the boundary of sigma, and it can move along the boundary of M, but it cannot leave it. And we're looking for the critical points of these functional, which is called, by the way, the volume functional critical points. And in order to find it, we're looking at the first variation, which is given by this formula. It has two terms, the integral over against sigma, and the boundary term. Here, X is the normal vector field on sigma as the section of the normal bundle. So I'm gonna identify sigma with phi of sigma with its image, and here H is the mean curvature vector, which is nothing but the metric trace of the second fundamental form. G, by the way, is the induced metric. There is some conflict of notations here. G bar is the metric in the, let's say that G bar is the metric on the ambient manifold, and then G is the induced metric. And eta is the outward pointing normal vector field along the boundary. So in my picture, it is, and as I have already said, we're looking for the critical points of this volume functional. And in order to do this, we need to solve this equation, delta V equals 0 for all, so for all normal vector fields on sigma. And it turns out that it is possible if and only if H is 0 in sigma, and sigma is perpendicular to the boundary of M along the boundary of sigma. One usually says that sigma meets the boundary orthogonally along the boundary of sigma. Let's consider some examples. The first important example is when MG is the ball centered at the origin of radius 1 in the Euclidean space, in the Euclidean unit ball. Euclidean space En, so I'm going to use the following notation for the Euclidean metric. Delta is the Euclidean metric. And the Euclidean space has very nice properties. For example, if you consider the if you consider an immersed surface in En, then it is easy to compute its normal, mean curvature. It turns out that it's nothing but the Laplacian of the induced metric G of the position vector. The position vector coincides with the image of sigma, so it means that nabla delta G of phi. By the way, for me, the Laplacian is nothing but the divergence minus divergence composition with the gradient. And the picture is like this. And what is also nice about the ball is that if you consider the boundary sphere of that ball, then if you want to find the normal something which is perpendicular to the boundary, then its tangent vector field is going to be proportional to the position vector field along. And this is the condition which we have here. Sigma means the boundary orthogonally. It means that along the boundary of sigma, we have that the normal vector field is proportional to the position vector field phi. And it is very nice because now we can rewrite in a very nice form the condition on phi to be a free boundary minimal immersion. This is I, FBMI. I will also use this notation. So this means that free boundary minimal immersion. So I for immersion. So this free boundary condition implies that the coordinate functions of phi, phi1 and so on, phi n, are harmonic in sigma because we wanted h to be 0. And along the boundary, we have the following condition. The normal derivative of phi I is phi I. And everybody knows, I think, that these Steklov, so these functions satisfy the following Steklov problem. And I'm gonna recall you quickly what is a Steklov problem. So sigma here is a Riemannian manifold, which is supposed to be compact. So compact, which has an empty boundary, which is supposed to be sufficiently smooth. And we're looking for harmonic functions in sigma, which satisfy this boundary condition. This number sigma, for which these conditions, for which this problem has a non-trivial solution, is called a Steklov eigenvalue. So Steklov eigenvalue, and the corresponding functions u are sigma Steklov eigenvalue, and u is a Steklov eigenfunction. And these eigenfunctions, these eigenvalues form the following sequence: sigma naught is 0, sigma 1, and so on, sigma n. They have a unique converge point of accumulation plus infinity, and they have finite multiplicities. And this set of eigenvalues is called the Steklov spectrum. And the Steklov spectrum is a very natural invariant of a Riemannian manifold with boundary. And you can consider the ith Steklov eigenvalue as the following functional on the set of Riemannian metrics, on sigma which assigns to each metric on sigma its ith Steklov eigenvalue. And this function is a little, is quite boring, because if you consider the homotheties, so if you multiply G by any positive number T, then it turns out that sigma I transforms in the following way. So it is sigma I of J T to the K minus 1. K, by the way, is the dimension of sigma equals K. So, and in order to improve this situation, we will consider the so-called normalized Steklov eigenvalue, which is going to be denoted as sigma I bar, which is also a functional on the set of Riemannian metrics, which assigns to each metric on sigma the normalized Steklov eigenvalue, which is actually sigma I j times the volume, so the volume of the boundary, the volume.
No, Vlad, I think it's just T minus 1.
Where
scaling.
Yeah, I think so. Yeah, thank you. Thank you. T to the minus 1, right? Yeah, I agree. The volume of the boundary with respect to the metric G, and here, so I hope here I write down the right exponent, right? So well, it should be, I think so. And Fraser and Shane prove a very nice theorem, which roughly speaking says the following. So if phi is a free boundary minimal immersion of a K surface with boundary into the to the unit Euclidean ball, then it happens if and only if the induced metric G is critical for the functional sigma I bar for some I. We don't know which exactly I. And critical means the following. So it means that sigma I bar of G of T is less than or equal to sigma I of bar of G plus little o of T, or sigma I bar of G of T is greater than or equal to sigma I of G plus little o of T. And here G of T is a smooth one parametric family of metrics depending on T. So smooth family of metrics. If your functional, well, in this this is our case actually, sigma I has derivatives d over dt when t left and right derivatives, then it is also, so then you can also say that your metric is critical for the functional sigma I if these the product of these two left and right derivatives is non-positive. And let me give you some examples of these free boundary minimal surfaces in the Euclidean ball. So the first example is very simple. So if you take K-plane passing through the origin, so K-plane, K-dimensional plane passing through the origin, then it hits our ball, and as a cross section, you obtain a K-ball, the flat K-ball centered at the origin, also with radius 1, and obviously it's a free boundary minimal surface in the ball. Another example, is also very simple. Everybody knows that a catenoid is a minimal surface in E3 in the three-dimensional Euclidean space. Then it turns out that you can rescale your your catenoid in order to get a unique catenoid which is orthogonal to the boundary sphere. And this catenoid is called the critical catenoid, and I'm going to denote it as K. So I know that the catenoid is spelled with C, but C is looks a little bit strange because it looks like a constant, right? So I decided to use K. By the way, in Russian it is spelled with K. So you can also find another example, non-orientable example of a free boundary minimal surface in the unit ball. So, but well, unfortunately, I cannot make a picture of it. So, because it's this surface lives in 4 dimensions, so it's impossible to picture it. It's a Mobius band, so you can do the same thing as we did with catenoid in E3. So you can take a minimal Mobius band in E4. There is a special Mobius band in E4, and you can find a unique piece of it which hits our boundary sphere orthogonally to it, and it's called the critical Mobius band. I'm not going to give you the precise formula because of these immersions, they are very well known, because it's not very important for my exposition. So well, and of course, there are many examples. You can find more information about them in the very nice survey by Martin Lee, and a very nice book by Lana Fraser about free boundary minimal submanifolds. But I'm going to consider now the following question. So free boundary minimal surfaces, despite their name, are not the points of minima, and they are just critical points. How do we work with critical points? We'll look at the second variation, and then we look at the Morse index of them. Let me recall you what the second variation, how it looks like for the free boundary minimal surfaces, for free boundary minimal submanifolds more generally. So I'm going to use the following notation. SXX is the following quadratic form. You see the very long formula here. Let me just explain the notation. Nabla perp is the connection, the induced connection in the normal bundle of sigma. Rx is a Ricci type operator, which looks as follows. So you take the Riemann tensor, EI is going to be the local orthonormal frame, and you consider on sigma, and you consider this guy. So this is exactly the definition of R of x, and B of x is the so-called Simon's operator, which looks as follows. So B, it is the second fundamental form of our surface, B EIEJ x, and you take the square root of it. And you take the summation over all I and j from 1 to k. It once again the outward pointing normal vector field along the boundary. This formula, in this generality, we don't use it. I'm going to use in the following situation when a codimension of sigma is 1. Then, by the way, you can find x, so you can express x as a function u times the normal to our surface. This is normal vector field, the unit normal vector field to our surface. And moreover, since En is flat, it is not curved, then you don't have the Ricci term. And our formula for the second variation simplifies. It takes the following form. So nabla G U squared, the length of it squared, minus the length of the second fundamental form squared, and minus the boundary term. And in order to define the, in order to work with it, we define the index of sigma, which is going to be the index, the Morse index of this form, quadratic form on functions. And it is going to be the dimension, the maximal dimension of a vector subspace of in the sections of normal bundle on sigma, on which this form is negative definite for any x in V. And the intuition here is as follows. So it is, you can also say that this is the maximal number of linearly independent infinitesimal variations, which decrease the volume of our free boundary minimal surface. So this is the intuition behind it. Let me give you some examples. So examples, the indices of the example that I have given you above. So the index of the k ball in the n ball is n minus k. The index of the critical catenoid is 4. It is this fact was proved by many authors. So De Viver, Tran, Smith, and Zhu, and myself. Just I thought that 3 proofs is not enough, and one need to find another one. So, and this fact, the index of the critical Mobius band is 5, which was proven by myself. There is in the case of sigma in B3, you can find the lower bound on the index, which was proved by Lucas Ambrosio, Alessandro Carlotto, and Ben Sharp, and also by Pamela Sargent. By the way, I don't know if I pronounce her name correctly. Maybe it is Sargent. So if you know, please tell me, because she's Canadian. And so here, gamma is the genus of sigma, and L is the number of boundary components of it. But this lower bound works only for 2 surfaces in B3. What about the upper bounds? The most general upper bound, which works for any free boundary minimal submanifolds, any compact free boundary minimal submanifold in any ambient Riemannian manifold, which was proven by Vanderson Lima. What are the terms here? So the index E, it is the energy index. So energy index. It turns out that there is another very nice functional on immersions on phi. It is called the energy. It is 1/2 of the gradient of phi squared. Sigma, and you can also find the critical, the first variation of the energy. By the way, its critical points are called the free boundary minimal. Free boundary harmonic immersions, harmonic maps. And you can also take the second variation, and the index of this form is going to be the energy index. So I'm going to give you the precise formula a little bit later. And the second term is nothing but the dimension of the moduli space of conformal classes on sigma. And if you don't know what is the moduli classes, the moduli space of conformal classes on sigma, so don't worry about this. This is a number which depends on the topology, and it takes the following form. It is 0 when the Euler characteristic of sigma is 1. It is 1 when the Euler characteristic of sigma is 0. And guess what's next? So it's impossible. It's 6 gamma minus 6 plus 3L for surfaces with negative Euler characteristic. So it depends only on the topology of sigma. What about another upper bound? So this bound, as I have already said, works with any free boundary minimal submanifold. Any free boundary minimal surface. Here it's important that sigma has dimension 2. But more general upper bound was on energy was proved by myself, and by analogy with the upper bound which was proven by Misha Karapukhin for closed minimal submanifolds in the sphere. So this upper bound works only for free boundary minimal submanifolds in the Euclidean ball of dimension 2. No, it's of any dimension, of any dimension. So here, this term n is the dimension of the ambient ball, and here this term is nothing but the spectral index. It is the number of Steklov eigenvalues which are less than 1. Because if you will go back to this problem, you see that phi I, the coordinate functions, are Steklov eigenvalues, are Steklov eigenfunctions with eigenvalue 1. So, and here we are interested in the the number of Steklov eigenvalues with eigenvalue less than 1. And this is the spectral index. And another lower bound was proved for hypersurfaces. So sigma has dimension n-1, also by myself, and the lower bound is well, it has two terms: the spectral index, and n is, as before, the dimension of the ambient ball. So, but we also have other very nice spaces. For example, the sphere, the round sphere, and the hyperbolic space, the so-called space forms. So it would be interesting to look at the geodesic balls in these spaces, and to answer the question: is everything that works with the free boundary minimal submanifolds in the Euclidean ball working for this setting? So let's consider free boundary minimal submanifolds in the geodesic ball, in a geodesic ball in the round sphere as n, and in the hyperbolic n space. Actually, I'm gonna consider only half of our sphere, the upper half sphere. So, which is going to be a subspace in the n+1 dimensional Euclidean space. It is given by this formula, the coordinates xi squared, the sum of them equals 1. It is nothing but the length of the radius vector equals 1. And similarly to it, Hn can be considered as the subset, the hyperboloid in the Minkowski space. So this hyperboloid is given by this formula, which is also can be considered as the square of the length of the radius vector equals -1. But here the Minkowski metric has signature, and G naught, this is the Minkowski metric, is going to be of the following form. Plus the sum xi squared I from 1 to n. So it has signature -1 plus, so minus, plus, plus, and so on. And we can take the following ball, geodesic ball centered at the point 1, 0, 0, 0. This is going to be our ball, geodesic ball, B N R, sorry, centered at the point P. Point P has coordinates 1, 0, 0, 0 of radius R, and R is the radius for the spherical case is less than pi/2, because we're living in a half sphere. In the case of the hyperbolic space, this is also geodesic ball centered at the same point 1, 0, 0, 0, and we can look for free boundary minimal submanifolds in that balls. So this is sigma free boundary minimal submanifold in this ball. So it meets the boundary orthogonally, and it turns out that in this case we also have a very nice description of these immersions, free boundary minimal immersions, which was first observed by Vanderson, Lima, and Lima Menezes, who made a very nice talk here in the seminar about a month ago, I think. So, and let's consider the similarity between these two descriptions. It turns out that the coordinate functions are of two sorts. The finite phi, the zero component of this immersion on the boundary satisfies the following condition: the normal derivative equals minus tangent of R phi naught. And the remaining component satisfies the condition the normal derivative equals cotangent R phi I. This is in the spherical case. In the hyperbolic case, you need to take not minus tangent, but plus a hyperbolic tangent, and not cotangent, but plus hyperbolic cotangent. And in place of k, you take minus k. K, by the way, it is the dimension of the surface of your manifold sigma, your free boundary minimal submanifold in the geodesic ball Bn. So let me give you some examples, also very simple examples. Like in the case of, in the flat case, you can take a geodesic ball, let's say in the sphere, in the half sphere, and you can take a plane passing through the origin of it, and it hits our sphere, and as a cross section we get a K ball of the same radius as the ambient ball, and obviously it meets the boundary orthogonally. The same picture or the same fact also holds for the geodesic balls in the hyperbolic space. We also have the following free boundary minimal annuli by I R. S lives in R, theta lives in S1, to B and B3 actually R. And well, the formula looks horrible, but it turns out that you can find a unique A, the parameter A, such that these annuli will meet the boundary of K orthogonally. So, these free boundary minimal annuli in geodesic balls were found by first by Morse, and they were also studied by Ducarme and Dacher. So Morse and Ducarme, Dacher, and I'm going to denote them by K plus for the spherical case and K minus for the hyperbolic case, because they look like, because they are analogs of critical catenoid in the flat case. If you go back to this formula, then we see that the coordinate functions satisfy the Robin problem. Robin problem is the following problem. So we're looking for the functions such that delta GU equals alpha U in sigma, and the normal derivative equals sigma U on the boundary. So you can actually change alpha, then you will get spectral curves, which are very interesting, and a lot of people study them. These spectral curves have asymptotics. For example, this is nothing but lambda 1, the first Dirichlet eigenvalue of sigma, and this is sigma 1, the first Steklov eigenvalue of sigma. But if you fix sigma, then you get a sequence of eigenvalues, sigma J alpha, which look like Steklov spectrum, but I'm gonna call them the alpha Steklov spectrum, and the corresponding problem is called the alpha Steklov problem. And it turns out that in the case when sigma has dimension 2, using these Steklov alpha Steklov eigenfunctions, by the way, for our situation, we will work with K Steklov eigenfunction for the spherical case, and minus K Steklov eigenfunction for the hyperbolic case. If sigma equals 2, then Lima and Menezes found a very nice functional theta R1, which takes the following form, which can be defined, which also depends on R of on the radius of some parameter R in between of 0 and pi over 2, and they also characterized. Well, they also studied the properties of this functional theta R1. Particularly, they found that the critical catenoid is so the metric on the critical catenoid on the sphere in the geodesic ball in the sphere is the maximal metric for this functional. I'm going to talk a little bit about this later. And it turns out that you can generalize it for any eigenvalue here. You can take sigma I in place of sigma 1. And by analogy to it, you can introduce omega Ri, sorry, when you take -2 in place of 2, and you replace cosine and sine by hyperbolic cosine and hyperbolic sine, and you need to take minus here. These functionals are actually, well, they look strange, but they are natural, because if you consider phi is a free boundary minimal immersion into the geodesic ball of in this upper half sphere or in the hyperbolic n space, free boundary minimal immersion, then the energy of this functional is going to be exactly twice theta theta r I for some I of sigma with the induced metric. G naught is the metric on the sphere, and in the case of the immersions into the hyperbolic space, then you take omega R1, Ri, sorry, sigma phi star G naught. And I was able to prove a theorem which is similar to the theorem of Fraser and Shane, which roughly speaking said the following: phi is a free boundary minimal immersion into the upper half sphere or into the ball, the geodesic ball in the upper half sphere or in the hyperbolic space, if and only if G, the induced metric, is critical for theta I or omega I respectively for some I. And Lima and Menezes actually proved some partial results. So some partial results. They prove it for in the case of maximal metrics, partial results. And in the remaining time, I will quickly explain what you can also do with these functionals, with this the description. So Lima and Menezes prove that sigma is, or if sigma is oriented, then theta R1 is actually bounded from above by this quantity. Gamma is the genus, and L is the number of boundary components of sigma. And the equality happens, so there is a rigidity part in this inequality. There is a which says that it happens if and only if sigma g is isometric to the ball B2R. So, and by the way, this only for the functional theta R1. So we can talk only about the free boundary minimal submanifolds in the geodesic balls in the upper half sphere. So it's not about the geodesic balls in the hyperbolic space. And I tried to generalize these results, and I was able to prove that if sigma is oriented, then theta Ri is bounded from above on the space of Riemannian metrics on sigma, and omega Ri is bounded from below on R sigma. And actually, omega Ri is always non-negative, and this lower bound 0 is actually sharp. And I don't think I have much time to give a proof. It's not very complicated, so I'm going to skip this part. You can ask me about the omega Ri is bounded from below, but is it possible to bound it from above? It turns out it is not bounded from below or from above omega Ri for any I and for any R. Moreover, you can also find, you can also prove that these functional, actually, this is exactly the proof. You prove that omega Ri is not bounded even in the conformal class, not bounded from above, even in the conformal class. In contrast to this, theta Ri is not bounded from below, even in the conformal class of any metric you take. So, so I also gonna skip this part. And okay, what you can also do with this description of free boundary minimal submanifolds, you can ask the same questions as I explained you in the beginning for the flat case. For example, about the index and index estimates. You take a look at the second variation of the boundary of the volume in the case when a codimension of sigma is 1. It takes this form. In the spherical case, in Sn, in the hyperbolic case, you need to replace n-1 by minus n-1 because of the negative curvature, and the cotangent r by hyperbolic cotangent r. The energy, I don't also think I need it. So, and then you can prove that, well, actually, I promise that I will explain what is the energy, the second variation for energy. It takes the following form. Here, you take V, any field, V, any field on B and on the geodesic ball of radius r, and you take the covariant derivative and take its length. And once again, because of the negative curvature, here we have minus k and here we have plus k. So this is for Sn, this is for Hn. And if you compare this formula with the formula for the this this variation, so this quadratic form, this is not variation, this quadratic form is the quadratic form for the index, the spectral index. The spectral index is defined in this setting as the number of the maximal dimension of linearly independent function u on which this form is negative definite. U star, U hat here is the continuation of U. U live, by the way, on the boundary. We can suppose that it is smooth. And it satisfies plus minus k plus for the spherical case and minus for the hyperbolic case. And du hat over d eta equals cotangent of r for the spherical case and hyperbolic cotangent of r in the hyperbolic case. And if you will compare this formula with the energy formula, then you will get the following very nice estimate, which was also true in the case of, in the flat case. The energy index is less than or equal to the n, the dimension of the ambient ball, times the spectral index. By the way, the spectral index for us, you can also define it as the number of eigenvalues of Steklov eigenvalues with eigenvalue less than cotangent in the spherical case, or less than a hyperbolic cotangent in the hyperbolic case. You can also prove the same formula which was also true for the flat case. namely, you can give the upper bound for the index in terms of n times the spectral index plus the dimension of the moduli space of conformal classes, and you can prove the lower bound, exactly the same thing what was for the flat case. And combining this, you can get almost for free that the index of the critical kind of analogs of critical catenoids in the spherical and in the hyperbolic case are for exactly the same value as in the flat case. So it is because the only thing you need to do here, it is prove that the spectral index of k plus minus equals 1. And this is the same as to prove that the number of Steklov eigenvalues with eigenvalue less than cotangent in the spherical case and less than hyperbolic cotangent in the hyperbolic case is exactly 1. The eigenvalue, this eigenvalue is exactly minus tangent r, which is in this characterization of components of the immersion of our free boundary minimal immersion. And you do this by ODE analysis, which is not very well, it is quite boring analysis actually, but not very complicated. And you can also find the index of the geodesic ball, K ball in Bn is n minus k. By the way, in my paper, there is a, it states that it is 2n minus k. It is wrong, actually. It is wrong. Actually, it is exactly n minus k, exactly like in the flat case. So I'm gonna update my the paper on the arXiv very soon with the correct proof. So the proof is pretty much less, pretty much is the same as written there. So and I'm gonna start. I'm gonna stop at these conjectures, which are also by analogy. Stated by analogy with the flat case, free boundary minimal immersions in the hyperbolic, in the ball in the Euclidean space. So we can suppose that these critical catenoids are the only embedded free boundary minimal annuli in B3, and K is the only immersed free boundary minimal submanifold in B3 of index 4. So the similar conjectures are known as Fraser-Lee conjectures, and they are not proved yet. So I'm going to stop here. So thank you for your attention. If you have questions, please feel free to ask them.
Thank you very much, Vlad, for the very nice talk. As just mentioned, if you have questions, you can either unmute yourself or just go ahead and ask. There's a question in the chat by Shakadar, who asks, how far does the notion of Morse index use here depend on the choice of variational field? Can we also capture perturbation which are not necessarily along the normal field?
Well, if you talk about the second variation of volume, then indeed you can take any perturbation, but it turns out that when you looking at the first variation, then you can only consider the normal component of them. So therefore, this question is if you take any vector field, then you can also consider, you can only consider its normal component, and you reduce the problem to normal variations.
Yeah. Thank you. Anyone else wants to ask something?
May I ask a question?
Sure.
Thank you, Vladimir, for your talk. So I want to ask you about this upper bound for this theta Ni and omega. So if you have multiple, I mean, the upper bound in term, do you have a formula in terms of the number of boundary component or something like that? For
in terms of the number of boundary components, so no, I don't have here. I can.
So basically, the asymptotic when the number of boundary component is like what Fraser and Chen.
Oh, yeah, it's still an open question. So if you take, I'm gonna provide an upper bound. So I'm gonna explain it, what the terms in this formula are. So it is some mysterious constant times sine squared. Sorry, it's not k, it is I in my notations. So I sine squared of r. It's a constant which actually goes back to the Grigoryan-Nitrusov-Yau very general estimate on eigenvalues of a Schrödinger operator. By the way, I'd like to thank Asma, who pointed out that I need to look at this paper in order to find this upper bound. So this constant goes from this very general estimate of Yau, Grigoryan-Nitrusov-Yau. And here is a very interesting question: how to find an explicit upper bound, like we did in the flat case, right? Well, not in the flat case, but for the functional, the normalized case Steklov eigenvalue, right? We have a bunch of estimates by Alexander, by Iosif, by Misha. So a lot of people obtained interesting results. So I would say that you can ask all the questions that we have asked for the functional sigma bar for the normalized Steklov eigenvalue here for these functionals. So there is a lot of work here.
Thank you.
Thank you. Any more questions? Comments? If not, let's thank Vlad again. Thank you for the nice talk, Vlad. So, and we will reconvene next week for a talk by Yevgeny Lyubomovich. We'll speak about parametric geometric inequalities and Weil law for the volume spectrum. Cool. See you all next week.
See you.
Yeah, thank you.
Thanks.
See you. Bye.
Have a nice day. Bye.